Okay, so far we've been finding derivatives, and we've been finding, like, updates for parameters and all that stuff, but particularly for one example at a time. We don't have multiple examples that are all together. Um, and I want to talk about that for a second, because it's a large part of deep learning is considering the computational resources that we have. And what ends up happening is that if we can parallelize, or basically do a lot of computations at once, we save a lot of time and a lot of energy. Um, and so how do we do that? Let's say we have, it's using this thing called vectorization. Okay, so as an example, let's say that our function is y equals wx. What this will do is it'll take an input x, and it will multiply that by some number w and give us our result. Now, let's say we want to do this for multiple values of x at once. So what we could do is, well, actually, let's say a simpler example is if we have two inputs, x1 and x2. So we have w1 x1 plus w2 x2, and these are combined to give us our value of y. Now, if you know about vectors, you'll know that this can actually be written as w1, w2, where this is actually a horizontal vector, or I guess a horizontal, like a 1 by 2 matrix. And a matrix is basically just a table. And then this is x1 and x2. So if you do this operation, matrix multiplication, then you would get w1 x1. So multiply this by this plus w2 times x2. And let's say you had a second example. So what you could do is just stack it stack it vertically, I guess. So you have x1, x2, and then this is your first example. Example 1, right? And I'll indicate this as my first example by putting a 1 in front. So this isn't 11, this is x11. So x11, x12, and then x1, x21, and x22. So there's a second example here. Example 2. So what I'm trying to prove is that you can feed in multiple things at the same time and still be able to get the correct outputs. So I've put a 1 in front just to show that it's the first example, and a 2 in front here to show that it's the second example. And then the second number just means which feature it is. So this is feature 1. So these are all correspond to feature 1 for their particular example. And this is feature number 2 for each of their examples. And now, based on this, you can calculate this as if you know about matrix multiplication, you'll know that if you have one matrix number 1, that is of shape PQ, meaning it has P rows and Q columns, and matrix number 2, which has shape RS. So R number of rows and S number of columns. Then in order to multiply these matrices, one thing is that has to be necessary is that Q is equal to R. The number of columns in the first matrix has to be equal to the number of rows in the second matrix. And as long as this is true, so this could be the shape QS as well. I could represent this as QS. As long as this is true, if we multiply these two matrices in this order, matrix 1 times matrix 2, the shape of the resulting matrix will be P, comma, S. So that is the shape of the resulting matrix. Now, we have we have this right here, which is a 1 by 2 matrix. So this is 1 by 2. And then this is 2 by 2. So if you have a 1 by 2 and a 2 by 2, this is the same, and the result should be a 1 by 2. So a 1 by 2, like this, where this first entry is just W1. So this first entry is W1 X1 plus W, oh, sorry, 1, 1, W2 X2, 1, 2, right? So what I'm saying is this times this plus this times this. And then the second one is W1 X21 plus W2 X22. And that gives us the result. What does this show? This shows that this would be our y hat for example 1. This would be our y hat for example number 2. If you notice, this is W1 times the first input feature plus W2 times the second input feature, all from the first example. This is W1 times the first input feature plus W2 times the second input feature, all for the second example. And so in this way, sometimes what computers allow you to do is you can do this computation W1 times X11 plus W2 times X12, and the computation W1 X21 plus W2 X22. You can do those both at the same time in parallel on different engines, essentially computation engines. And so since you're doing those in parallel, you could do this faster instead of like waiting for one to finish and then doing another. And so that's why I encourage you to think about this as more in terms of vectors and matrices rather than individual examples. But when you're thinking about derivations like the cost function derivative and other things like that, I think it's helpful to think about just one example at a time, and then it extends easily to other examples. But when you're thinking about your data set as a whole, you shouldn't be thinking about just one example. You should be thinking about maybe my data set can be represented in a table, which is essentially a matrix, which let's say there are 10,000 examples, 10K examples, and 10 input features. So for each of the 10,000 examples, I have 10 input features, and then my y is, there's just one value for y, and then there are 10,000 y values, each corresponding to one of the examples in the x, right? So this would be x, and then this would be y, and what you would have is w, right? And let's figure out what the shape of w is going to be. So let's say you have w times x is equal to y, right? Y equals wx. Like over here, right? This essentially could be called capital W, and this could be called capital X, since it stores a lot of values of x. And over here, in our example, this was of shape, this was 1 by 2, 1 by 2, and this was of shape 2 by 2. And the resulting y value was of the shape 1 by 2. Because of this 1 and this 2, you get the 1, 2. And that means that each of the columns of y corresponds to a separate example that comes from x. Okay, so now let's say that you have a bigger data set, right? And this was 10,000 examples and 10 input features, and then there's only one output feature. So we want to know, what is the shape of W going to be like? Well, we don't know the shape of W, right? So let's say this is P and Q, but we know the shape of X. It's 10,000 by 10, and Y has the shape, if we store everything in, these examples are actually stored in rows, let's store them in columns. So this would actually not be 10K over here. It would be just 10 here, and it would be 10K on this side. And this would not be like this. It would be more like this. So this is Y, and each column corresponds to one of the 10,000 examples, and there's only one row because there's only one possible output. So in that case, I should actually fix this up and change this to 10 by 10,000. So there's 10 rows over here and 10,000 columns, each corresponding to one of the examples. And over here, there's one row and 10,000 examples. So let's write that down. 1 by 10,000. And so in order for us to be able to multiply this W and X, this has to be the same as this. The number of columns in the first matrix has to be the same as the number of rows in the second matrix in order for matrix multiplication to even work or to be defined. And so that means that Q is equal to 10. What's more is that the resulting shape of this matrix multiplication, given that Q is 10, is going to be P comma 10,000. And since that is equal to Y, which is 1 comma 10,000, P is going to be equal to 1. So essentially W is just this 1 by 10. So this is 1. And then this is going to be 10. This is a 1 by 10 matrix that is just filled up with things like W1, W2, W3, all the way to W10, right? And let's take another example. Let's say there was not just one output, but there was actually two outputs. So there's a Y1 and Y2. So now all that's changing is that you have a bigger Y, which has two rows and 10,000 columns. And then X still has 10,000 columns. So this is still 10,000. This is still 10 input features. And we want to figure out if Wx is equal to Y, then we want to figure out what is the shape of W. So let's say this is P comma Q, just like before. And X, the value of X is 10 comma 10,000. And the shape of Y is 2 rows and 10,000 columns. So from here, just like before, Q has to be equal to 10 in order for matrix multiplication to be defined. And for P has to be equal to this first thing over here, which is 2. So therefore, W actually has, W is actually 2 rows, right? W1, all the way to W10. And there's a second row, which is W, let's say 11, all the way to W20. And I can be more precise, actually. Let me take that back. I don't want to do W11 all the way to W20. What I'll do is I'll do W11, W12, W13, all the way to W110. So I'll just add a 1. It's not 110, it's or 11 or 12. It's 1, 2. The 1 meaning that I'm using it to calculate the first output, the first Y output. And this one is, let's say, W21, W22, all the way to W210. Again, this is not 21, but it's a 2 attached before the 1 to indicate that we're using this row, this whole row of W's corresponds to computing Y2, whereas this one corresponds to computing Y1. And this is what we multiply by the first input feature. First feature at any given time, no matter what the example is. And then this is let's say the 10th feature. Not, I didn't mean what the example is at any given time. I meant no matter what output we're computing for. So now this essentially tells you that um, we can store all of these computations like matrix multiplication, sorry, in matrix multiplication format. So if we're doing a neural network, right, and we have a lot of input features, and we have, let's say we have three things that we're computing, but we have five inputs, right? So five inputs and three things that we're computing. We don't have to store this all as W1, W2, W3, W10, whatever, right? We can store it in a matrix format, right? Instead of storing them individually, we can store them all in matrix format. And our input size would just be so the size of X, right? Our goal is that this is Y, and then that this is X. And whatever is used to get from X to Y is W. This is actually called a linear transformation and in linear algebra. But if Y is equal to WX, and the shape of X, let's say we store all of the examples in columns. So the number of features, which let's say is not 10, sorry. You have 5 input features per example, right? Because of these 5. And then you have 100 examples, right? Each one example is stored in the column, right? So the first number that you have for the first input feature, second input feature, third input feature, fourth input feature, fifth input feature, and then that's all one example. Then the second example and third example and so on and so forth. And then your Y is, let's say, there are 3 outputs, right? So that means that this is 3. And the number of examples, it should be 100 as well, right? That should be the output. So we want to find the shape of W. And just like before, this should be 3, comma, 3, comma 5, right? So this would give us, so this has to be the same as this, and then 3 is the same as that 3 over there. Because when you multiply W by X, the resulting shape would be 3 by 100. So um, in this case, W has 15 values because its dimension is 3 by 5. There are 3 rows, 5 columns. Each of the rows correspond to calculating, correspond to a different formula for calculating each of these 3 outputs. And each of the columns corresponds to how do we use each of these input features at any given time. So if you're in the second row, but in the third column, what this would do is it would inform you of how are you going to use the third feature and in order to compute the second output. Okay, that's essentially what it means. And over time, you'll get used to this notation of matrices and stuff. But I want you to notice one thing. The shape of our W was actually had nothing to do with the number of examples. It was the output dimension, which is 3, right? Whatever we wanted outputted. And the input dimension is 5, which is whatever the input dimension is. And so that will be the shape of your W, right? If you go from 3 to 5, 5 to 3, it'll be 3 by 5. If you go from 3 to 10, it'll be 10 by 3. If we had a layer with 4 after this, right? And we connected that, then the shape of this W that corresponds to going from this layer to this layer would be 4 by 3, and so on and so forth, right? But now I hope that you've gotten this idea that we're not talking about just numbers anymore. We're talking about entire tables. And as you get larger and larger data sets, you'll need to organize your data as tables, and it'll be harder if you don't, because it's harder to generalize to more examples like neural networks and other things. Um, but that being said, there's only one other thing I wanted to talk about with you at this point, and that was how do we initialize the parameters for W in any given scenario? So in terms of neural network, so logistic regression and linear regression, we did 0, right? We just initialized all of our parameters, be it W1, W2, W3, so on and so forth. We initialize them all to 0. But for neural networks, we have to do this thing where we initialize them to random values. Random values, we could just do them random between 0 and 1. It doesn't matter, but they sort of just have to be different values, right? And that's because of a symmetry problem. You can work this out yourself, but if everything was initialized to 0 in this case, then the computation for this would be the same as the computation for this, and the same as the computation for this. And the point of a neural network is, as I said before, that we're doing some internal computation to do some feature processing. But then essentially, if every weight is 0, all of the W's are 0, then this will be 0, this will be 0, this will be 0. And essentially, you'll be computing the same function for across all of these hidden computations. And so they're not computing different things or adding any additional value. They're sort of just one value, and they're not sort of breaking symmetry. That's the term for it, breaking symmetry. Um, and that, yeah, that's why you would need to initialize on a number, 0 to 1. It could be based on the random distribution or like normal distribution, which is the bell curve like this, which I drew horribly. But you could sample from the bell curve, and there's more ways that we can talk about later about how to initialize. But you can't initialize to 0 for neural networks in general. So I guess that's all I wanted to talk about in this video. So thank you.